US Physics Olympiad year 2010 USAPHO Semifinal. Problem B2. These three parts can be answered independently. Part A. One pair of ends of two long parallel wires are connected by a resistor. Resistance equal 0.25 ohms, and the fuse that will break instantaneously if I0 current through it equal 5 ampere of current passed through it. The other pair of ends are unconnected. A conducting rod of mass m small is free to slide along the wires under the influence of gravity. The wires are separated by L equal 30 centimeters and the rod starts out distance A equal 10 centimeters from the resistor and the fuse. The whole system is placed in a uniform constant magnetic field of B equal 1.2 Tesla, as shown in the figure. The resistance of rod and the wires is neglectable. When the rod is released, it falls under the influence of gravity, but never loses contact with the long parallel wires. Questions. 1. What is the smallest mass needed to break the fuse? 2. How fast is the mass moving when the fuse breaks? Solutions. First, what is the smallest mass needed to break the fuse? Let's count it. When we have a rod which is free to fall under gravity, it will start to accelerate, but because it's moving through a magnetic field, due to electromagnetic induction, there will be EMF created to decrease this acceleration, and there will be current through this rod which is going to the direction to reduce this change of magnetic flux. So it means that from a magnetic field we will have a force acting in opposite to motion way, and we can just write this equation that after a certain time this rod will reach the terminal speed. We will have mass multiplied by g, which is force of gravity, must be equalized by force from magnetic field, which is BIL. In our case, maximum current is I0, so it means that we can count what is mass needed to break this fuse. That will be this one. So mass equal magnetic field multiplied by length of rod multiplied by maximum current and divided by g, gravity acceleration. So that will be finally 0.18 kilograms. That's the answer for first question in this part. Second question. How fast is the mass moving when the fuse breaks? Now let's count what is the speed. When this rod moving with some sort of speed, that will create EMF due to change of magnetic flux, and this EMF could be counted by this way. EMF equal change of magnetic flux through a certain time. In our case, magnetic field is constant, so that will be change of area under certain of time, and that will be just magnetic field multiplied by length of this rod multiplied by speed of this rod. we know that EMF equal current multiplied by resistance. In our case, we know that maximum current is I0 and resistance is 0.25 ohms. So now we can count what is speed. Because from the other hand, EMF equal I0 multiplied by R, we have for speed this equation. That's equal I0R over BL. When we put numbers, we will get 3.47 meters per second. That's the terminal speed of this mass. Part B. A fuse is composed of a cylindrical wire with length L and radius R much smaller than L. The resistivity, not resistance, of the fuse is small and given by ρ fuse. Assume that the uniform current I flows through the fuse. Write the answer below in terms of L, R, ρ, F, I, and any fundamental constants. First question. What is the magnitude and direction of the electric field on the surface of the fuse wire? Second question. What is the magnitude of and direction of the magnetic field on the surface of the fuse wire? Third question. The Poynting vector S is a measure of the rate of electromagnetic energy flow through a unit surface area. The vector gives the direction of the energy flow. Since S equal 1 over mu 0 multiplied by cross product electric field by magnetic field, where mu 0 is the permittibility of free space and the E and B are electric and magnetic field vectors, find the magnitude and the direction of the Poynting vector associated with the current in the fuse wire. Solution. Suppose that our fuse is going inside of this page and the current going inside of this page. It means that the electric field must go inside of this page. And we can write equation for Ohm law for this fuse. Potential difference between ends of this fuse, U equal current multiplied by resistance of this fuse. But resistance equal resistivity multiplied by length L and divided by area of cross section, which is pi r square. And from this formula we can find what is electric field. That will be potential difference divided by length. And finally we have electric field equal current multiplied by resistivity of this fuse and divided by pi r square. Now magnetic field we can count from Ampere law. If we have a wire with the current I and the radius r, on the surface of this wire we have magnetic field equal this expression. And if current going inside of this page, magnetic field is going clockwise. And from these two directions, electric field going inside of page and magnetic field going clockwise, we can count what is the magnitude and the direction for Poynting vector. That will be this expression, 1 over mu 0 multiplied by cross product. In our case, electric field and magnetic field, they are perpendicular to each other, so it means that we can count full cross product like this. And due to vector cross product direction, we have direction for this Poynting vector is going inside of this fuse. so it will get hotter during the time. So we just answered for all three questions for this section B. Part C. A fuse will break when it reaches its melting point. We know from modern physics that a hot object will radiate energy approximately according to the blackbody law at power equal sigma AT power 4, where T is the temperature in Kelvin, A is the surface area, and sigma is Stefan Boltzmann constant. If T fuse equal 500 kelvins is the melting point of the metal for the fuse wire with the resistivity ρ equal 120 nano-ohm by a meter, and I fuse equal 5 ampere is the desired breaking current, what should be the radius of the wire R? Solution. So from one point we can count what is total power which is absorbed by this fuse from pointing vector. That will be P equal pointing vector multiplied by side area of this fuse. From other point we can count what is power emitted by this fuse as a blackbody radiation. That will be this expression. So now we just can equalize these powers. So this side area is cancelled, and we have equation that pointing vector which we count earlier equals sigma T fuse power 4. From here we can count what is the radius of this wire. That will be this expression, and after when we put numbers we can count what is radius. That will be 0.35 millimeters. That's the answer for part C.